Hello, this video should help you to derive a formula for the position or to calculate the position of the maximums of the interference pattern when you're using a diffraction grating. So I won't go too much into detail here because we've already done a similar derivation for the double slit experiment. So the difference is not as big, but this is just another way of repeating that and extending what we've already learned. So just a quick remark that the phenomena can be explained by using Huygens principle. So, for example, if we put the elementary waves here, and what we've already done will lead to the same result, that we've got a number of maximum points here on the screen. So this one here will definitely be a maximum. It's called the main maximum, or it's got the index 0. And then we've got, for example, the first one is here and the second one is there, and then on the other side it's the same thing here. So then if you look at the index n, for 0 it's the main maximum. If n is 1, then we've got the first maximum. This could be the second maximum, for example. So before we begin, I would like to mention that again we use some approximations, and as you can see here, we assume that the, let's say, light rays are parallel to each other in the on the left side here, but then again we assume that they meet in one point, so they can't be parallel. This is due to the fact that the capital D is very big considered to, well, the distance between two light rays, for example. Then again, the point AN is definitely not a mathematical point with 0 dimensions, because then we couldn't see it. So it has a little extension. That means that, well, reality is somewhere in between anyway. So yeah, this is just the information that we need in order to derive the formula. Okay, so what's happening now? I think it's hooked up. Okay. It takes a little bit longer, nevertheless. Here we go. Okay. So, as we know, the sine of the angle, and here we've got alpha n, where n again is the order of the maximum, is our delta S. So it's the path difference. I'll explain it again in a second, by D. So what we do here is we look at one of these little triangles As you can see further down, we've got the angle alpha n, and the opposite side is delta S, and then we've got the d delta S. Here's the angle. So yeah, that's about it. So we've got this slit separation, and oh yes, and delta S, to say it again, is when you look at it at the distance that the first light ray is traveling, the second light ray has to travel a larger distance, and it's larger by this delta S. And we've seen before that if delta S is a multiple of the wavelength lambda, we have constructive interference. That means a maximum. And of course, if n is 0, we end up here, which makes sense because delta S is 0 and alpha sine of 0 is 0. So as we increase this delta y and we go up, we find somewhere a location that's called A1, where this delta S is exactly one wavelength. That means that's the first place where we've got constructive interference. And when we go further, let's say this is n equal 2, then this delta S would be twice the wavelength. And then again, we've got constructive interference, as we know. So just one more time. Why is this the case? We've got two waves, and this kind of represents the main maximum, where the path difference is 0. So the waves start at the same time on the same, let's say, starting line. But if we move the second wave and we shift it by one wavelength, then we've got the situation again that crests and troughs are on top of each other, so they meet in the same location. Okay, more or less here in my drawing. So then we've got delta S is lambda. And if we do it again, shift it again by lambda, we've got delta S is 2 times lambda, and again we see that the crests lie on top of each other. Okay, so we take the first equation, and we can say that the d, bring that to the other side, so we've got d times sine of alpha, and now we replace the delta S by n times lambda, which is the condition for a maximum, for the nth maximum. And now if we put the n on the other side, then we've got d times sine of alpha over n. So that's a formula. hang on, where how we can calculate the lambda. Now, because what's the purpose of all of this? It could be that we use the light of a certain light source. We've got the grating and we can measure the distances, meaning the distance between the grating and the screen, the distance delta y between several maxima, and what is normally given is the small d, so the slit separation. And that these three lengths allow us to calculate the wavelength of the light that we have been using, because otherwise it's going to be difficult to measure the wavelength. So that means we have to determine it by this experiment, for example. Now we've got the n is obvious, that's visible, which n we have to put in. The d is given to us, but the sign of alpha is a problem. So that's why, again, we say for small angles, like this is here, we've got 10 of alpha is delta y over the d. Now we've got a different triangle here, which is this one. Where we've got the alpha here. Well, it should be somewhere in the middle. It makes no sense down here. So, but the delta y is the same anyway. So, yeah, we've got this triangle here, basically. But so what we've done before, we say that sine is almost the same as 10 of an angle, of a small angle. So we can replace the sine of alpha again, and we end up having d times delta y over n times d. And now we've got the three lengths that we can measure or that are given to us, and the n which we can count. And this formula is now giving us the possibility to calculate the wavelength of the light that we used. So there's just one more thing that sometimes, or I would say very often, it's not the slit separation that is given to us, but it's something called grating constant. So for example, it's called G, but in literature sometimes the D and the G is mixed up, and in English literature it might even be different notation. I honestly don't know. I would have to find out, but we will see once we look at the questions in the book. It should be obvious, but you should know the difference. So here this constant is, for example, telling us that there are 1000 slits per millimeter, so divided by millimeters, so 1000 slits per millimeter. That means if we want to find out the distance between these, we have to take the reciprocal value, or the inverse, which is then 1 over 1000 millimeters, and that is 1 micrometer. Yeah, this is a typical slit separation space. So yeah, that was the whole idea to derivate this formula.